Hi everyone. So the aim is to derive the Black Scholes delta using a much simpler method. We have derived the delta using a couple of different approaches before. The method we are going to cover in this video will use similar maths concepts but far fewer math symbols and steps. So let's start at the beginning. As you know, Black Scholes assume that the stock price follows the geometric Brownian motion process. There is a drift element to the dynamics which under the risk-neutral measure is equal to R, the risk-free rate, but let's ignore the drift to keep the presentation simple. Including the drift won't change a thing, but it will just involve writing a bit more, so we go without the drift. In terms of probability distribution, the dynamics means the stock price at a given horizon will be log-normally distributed with mean and standard deviation as follows. Let's assign values to the parameters to make things more concrete. So let's assume that the initial stock price is equal to 10, the volatility is equal to 40%, and we are interested in an option with 1 year maturity. If you plug in these values into the expression for mean and standard deviation, you will get mean of 2.22 and standard deviation of 0.4. The current stock price is 10 and the price 1 year from now can be anything between 0 and infinity. To plot the distribution, let's divide the interval into sub-intervals of length 1. We have grouped everything above 35 into one group, and then using the log-normal dist function and any spreadsheet tool, we can calculate the probabilities of the process taking values in these intervals. We can assign the average value to each interval. The interval from 35 to infinity is tricky. Infinity divided by 2 is infinity, but the effective average comes out to be 39. Now if you multiply the values by the probabilities and sum across the intervals, you will get 10, which is the current stock price. Notice here we are showing the product for alternate intervals. For example, this range covers 4 intervals, but we show the multiplication for only 2 of them. It's just to make sure things stay visible. Now let's consider a European call option with strike price of 10. The option won't pay anything if the stock price at maturity happens to be lower than 10, so these intervals won't contribute, and we can thus discard their contribution to value. And the payoff and the remaining intervals would be the difference between the stock price at maturity and the strike price. Probabilities stay unchanged. Now if you multiply and sum across the intervals, you will get 1.59, which is the price you will get if you plug in the parameters we have chosen into the Black Scholes. The payoff of the European call option depends on the price of the stock at maturity, and we are interested in the mathematical derivative of the current value of the payoff with respect to the current stock price. We explored the link via the explicit relationship between the current and at maturity prices of the stock, which is given by the solution of the GBM SDE. The relationship, in addition to the deterministic quantity sigma and t, contains the random quantity W. So for a given initial stock price, the terminal price will be a random quantity which we already know will be log-normally distributed. Let's say we have one realization of the W which translates into S taking the value between 11 and 12. The option payoff under this scenario would be S minus K if S is greater than K. If the initial stock price had been a bit higher, say by amount delta S naught, then the stock price at maturity would be as follows. We just replace S naught by S naught plus delta S naught, and we represent this stock price by S tilde. It means the same realization of the Brownian would have produced a slightly higher stock price, and the option payoff would have been this S tilde minus K. Again, the option only pays if the stock price is higher than K, which is the case here. If we plot the probabilities of this shifted process on the same axis, then for the given parameters, the probabilities of the intervals we have displayed will be higher. The intervals we have displayed here form the and the money range of the call option. So the increase in probabilities we see here will be offset by the decrease in the out of money range which we have discarded. And the increased probability means the call option payoff under the shifted process would be more valuable. Now the indicator function in the two payoffs are different. This one has S tilde. But if we let delta S naught go to 0, then the two will differ over negligible range, the probability of which will be almost 0. So we can align the indicator functions. Now we can easily calculate the difference between the two option payoffs for the given realization of the Brownian. The K's cancel, and hence the difference is just equal to the difference between the two stock prices if they are greater than K and 0 otherwise. We can express this difference in terms of the underlying parameters and source of randomness, which is the Brownian. We use the expression for the two prices, so the S naughts cancel, and we are left with delta S naught times the exponential term. We can shift delta S naught to the left hand side, and we then have to divide the option payoff identity by the same delta S naught. And we can now replace the stock price term on the right hand side. Now if we shift S naught to the left hand side, we see the exponential term is equal to S divided by S naught. And if we let delta S naught go to 0, then the left hand side is just the derivative of the payoff with respect to S naught. This identity holds for one realization of the Brownian. If we had another draw, the S's would have been different, but this identity shall hold. If we do large number of draws, then the relative frequencies of S will match the distribution we have here. To compute a single estimate, we take probability weighted average, which is really the expected value. The expected value is just the first component of the European option price, which under the Black Scholes assumption is equal to S naught times N of D1. The S naughts cancel and we are left with N of D1. And we have derived the Black Scholes delta. Please give a thumbs up if you would like to see similar videos, and I look forward to seeing you in the next.